Hello guys, welcome back to my YouTube channel. This is Dizzy Structures, and today we are going to be dealing with shear stresses in beams. Let's dive into it. So, shear stresses in beams. And yeah, before I start, I would like to draw us back to bending stresses, which we did last session, year 2, it's on the level second semester. We took the course bending stresses in lag, and I learned that in bending stresses, the assumption they made rather was that the bending moment along the beam is constant. And if that's the case, if the bending moment is constant along the beam, it means that the shear force will be 0. That is, it means that consideration of shear force is not included. That is, it means that consideration of shear force was neglected. It means that shear force was neglected. So today we're not going to be neglecting our shear force, which in turn means that we're not going to be neglecting our shear stress. Reason is because now we're assuming that the bending stress is not constant. Now that we're assuming that the bending moment is not constant. Now we're saying in essence that our bending moment or our bending stresses is actually varying, which is most likely the case in real life phenomenon. So what we're saying is that, okay, if this is a prismatic rectangular section of a beam, and we cut our beam here, cut it here, and we do the same thing, we cut it. So it means that we're having these two sections. We're having this section. Let's zoom in on it, separated by distance dx. And this is the section we cut. This is the other section which we cut. So what I'm saying in essence is that now we're saying that the bending stress is actually varying. So I won't have the same value of bending stress that I had here. It is varying by an amount, the sigma. So when you see something like this, it means that shear stresses must or cannot be neglected. They'll have effect. So what does it mean for shear stresses to have effects when this arises, when our bending moments or our bending stress varies? It means that the layers of the beam, let's say we assume that the beam is made up of layers stacked upon layers, layers stacked upon layers, layers stacked upon layers to form the beam. Layers, forgive my drawing, but just you get the concept. Just think of a beam formed like layers, 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 layers. So what I'm trying to say is that when the bending stress is varying, that is when shear stresses arise, it means that this effect would want to make the layers of the beam slide apart. Slide apart. They would want to make the layers of the beam slide apart because of the varying bending stress. So let's derive the formula, and I believe that as we derive the formula, we would get a better understanding of what we are doing here. So let's go. So once again, this is our cross section, or the cut section, rather the cut section of the beam that we just did, but the enlarged view. Separated by distance dx. This is another section. Now, of course, this is really our neutral axis and the imaginary line with zero bending stress. Yes. What am I missing? Yes, nothing. So, if I come to you and I say, hello, DG Structures, analyze, or I want to know what is going on in this section of the beam or within this layer of the beam. I want to know what is going on within this layer of the beam. If I come to you and tell you that, it means that first of all, there will be a distance from this layer to the neutral axis. We call this distance y1. And it means that there will be an area above, that is an empty space above this axis which we are analyzing. Let's say axis EF. So now with simple mathematics, with integration, I can assume that this area is made up of cylinders, long thin cylinders, which eventually will fill the space. And if it is made of cylinders, it means that, okay, it will extend itself, this will extend itself, and so on and so forth. Right? So, let's say I just want to, for the sake of simplicity, I just want to analyze one cylinder. Just one. I remember the cylinders make up that area, but I just want to analyze just one. That is, now the area will be dA, since I'm analyzing just one. The area of the cross-section of the cylinder will be dA. Now, the distance from the center of dA to my neutral axis the distance of the center of dA, that is the center, this distance here, up to my neutral axis, which is NA. I will call it Y bar. Or no, let me call it Y, since it's, it is Y bar when it is the total area, but let's use Y since we're just representing, or we're just using it to, we're just using one cylinder, one, for the sake of simplicity. But at the being, it was now the total area, we'll be using Y bar. But since it is not yet the total area, we're still using Y. If you can remember, A Y bar is equals to A1 Y1 as plus A2 Y2 and so forth and so on and so forth. This Y bar means for the whole, but this Y is the same as this Y bar, but this one is just for simplicity, for just like one or something. So that's just the difference. So instead of Y bar, let's use Y. At the end of the day, it will be Y bar when we are now having the total area in that enclosed space. So once again, the distance from the center of dA of this cylindrical cross-section to the neutral axis is called Y. While the distance from the points or the axis that we are analyzing down to the neutral axis is called Y1. Please, let's remember these guys. So the next thing that we need to put in mind is that we need to go back to the fact that the bending stress is varying. If the bending stress is varying, it means that all my area here in this section will be of sigma, and in this section, I'll be having a stress of sigma plus d sigma, a different stress entirely. Like I think I explained it here. Exactly, I explained it here. It's varying. It just basically means that the stress is varying. Just think of this as another stress, but a new type of stress. It has varied. It's different from this stress. So now at section, let's call this A, let's call this cross section A and cross section B. At cross section A, now I'll be using my bending equation, m over I is equals to, everything just links. I can now see the importance of last semester, or rather last session. So now m over I is equals to sigma over y. I won't be needing this. I'll use this, which is what I have. So, since this is the sigma I'm looking for, it means that my sigma will be, sigma is equals to my over I for section A. I for section B, phase B, phase B, guys. So I'll be having sigma plus d sigma because to the same thing will be equals to m plus dm y over I. Sorry for the noise, guys. I'm not home alone. So it's just the same thing, but you know the formula was sigma equals to my over I, but because of the variation, so it's now like saying this is sigma plus this, sigma plus equals to m plus, so it's just variation, guys. In essence, I can just think of this term here as a single sigma. I can just think of it as a single sigma, but I will have it at the back of my mind, maybe sigma 2, that, okay, this sigma has varied and it is different from the sigma that we did before, which is sigma 1. It will be equals to m plus dm y over I. So, I recall now, you can see that we have done for phase A and we have done for phase B. But now, recall that force is equals to stress times area. And in this case, since we are dealing with just one cylinder, it will be force is equals to sigma times dA. Let's continue in the next video, guys.